Okay, hello everyone. Let's welcome you all to this session of the course Fluid Dynamics for Astrophysics. We are very much near to the end of the course, so and I hope the videos are getting fruitful for you, and you guys are well prepared for your exam, and guys are doing well in your assignments. So it will be helpful, more helpful for me if you join the live classes. But anyway, so I understand your timing. So without further ado, let's do some recap and course session, assignment and problem solving. Let me share my screen. So the last time doing the sample questions answer. Now we are doing the assignment 6. So now we have some model questions. Don't have much time, so we'll start from here. So the question number 1 is: a rocket is designed to generate a thrust of 30,000 Newton, operating at an altitude of 20 kilometers. So, so then, okay, I think for operating at an altitude of 20 kilometer, where the pressure is 5467 Pascal. The pressure inside the combustion chamber is 1000 kilopascal, where the temperature is 2500 Kelvin. The gas constant of the fluid in the jet is R 280 meter square second inverse square Kelvin inverse, and gamma is 1.4. The Mach number of the flow at the exit of the nozzle is 4.15, density is 0.0347 kilogram per meter cube, and the temperature is 562 Kelvin. So then what is the speed at which the gas exits the nozzle? Okay, this is simple. You have the equation. It's not simple, but if you derive the equation with the shock conditions, and inhibitory conditions, and you get the speed, the post-shock speed with the Mach number. So you know Mach number is defined as U by root over CS, U over CS. So then U is Mach number times CS, and CS is root over gamma P by rho, and P is then get T, or you can define by rho R T. So it will be just gamma R T. Putting this value, Mach number is given. Mach number is 4.15. Okay, and gamma is also given 1.4. R you know that 8.314, and T is, you know, T is given 2500. So you can easily calculate, and you'll get approximately 1948 meter per second. So these other values as force and altitude is not useful here, but this is to check your knowledge and the ways of the seminar. Some condition for density on either side of a socket. Rho 1 by rho 2 is this, and that for the pressure is this, P2 by P1 is this. But gamma is the ratio of specific hits. For monatomic it is 5 by 3. The subscript 1 refers to the pre-soaked gas, and the subscript 2 refers to the soaked gas. The quantity M refers to the pre-shock Mach number. Based on this information, pick the statement that are correct. For M much greater than 1, the pressure ratio P2 by P1 is proportional to M square. For M greater much greater than 1, this is simple. You can just simply put M much greater than 1. So if you put M much greater than 1, this term will be negligible. This term will be 0. Okay. And here also, if you put a much greater than 1, you can't put directly. You should better divide it by M square. So 2 gamma minus gamma minus 1 by M square, this term will be negligible. And then there will be also, okay, let me personalize this. Temperature can also be calculated. So for A much greater than 1, the P2 by P1 is proportional to M square, right? Because the other terms will be negligible. Gamma minus 1 by M square will be 0. Gamma plus 1 by M square will be small. So it will be proportional to M square only. Or you can think about like this, 2 gamma M square by gamma plus 1. Okay. So and minus gamma minus 1 by gamma plus 1. This is a constant, so it will be proportional to M square. B is not true. As you see, the inverse of it, it is constant actually. It doesn't depend on M square. C for a much greater than 1, temperature ratio proportional to M square, because if we put the P is equal to NKT relation, you'll get that it is also similar to P2 by P1 and P is equal to NKT, P proportional to T. And D from mass conservation, the velocity ratio U2 by U1 is equal to 1 by U2. I've already gotten that, right? That rho 1 U1 is rho 2 U2. Okay. Pick the correct statement. A supersonic to subsonic transition has to necessarily involve a shock. A supersonic flow transitioning through a shock always transitions to a subsonic flow. If the entropy of gas that had passed through a shock is the same as that in the pre-shock flow, the entropy of gas that passed through a shock is larger than the pre-shock flow. Okay, supersonic subsonic transition doesn't involve a shock because a shock always results in a supersonic to subsonic transition. Right? A shock always results in a supersonic to subsonic transition. However, supersonic to subsonic transition did not always involve a shock. There can be solutions that pass smoothly through the critical point. The supersonic flow transition through a shock always transition to a subsonic flow. Basically, supersonic flow, when transition to subsonic, it has to go through a shock, but it doesn't mean that a supersonic to subsonic involve a shock. Okay. Solution, the and a shock generates entropy. So the post-shock gas has a higher entropy. Option B and D are correct. You're in a situation where you are trying to determine the Mach number of a young shock. You know that it's a normal shock and that its Mach number is certainly larger than 10. You would like to make a more precise estimate of its Mach number, whether it is closer to 20 or 50. You can do this if you have access to the density jump back to the shock, you have access to the temperature jump back to the shock, you have access to the pressure jump back to the shock, or you have access to the velocity jump back to the shock. For a strong shock, specifically Mach number larger than 4 to 5, the density and velocity jumps are intensity to the Mach number. The pressure and temperature ratios, however, always contain the Mach number. Okay. So option B and C are correct. In fluids, a nozzle is generally defined as a device which takes a relatively slow speed fluid stream and converts it into a high speed stream. For instance, you pinch a garden hose pipe which has water flowing in it, you are creating a nozzle. The diffuser, on the other hand, takes a relatively high speed stream and slows it down, diffusing into a large area. For instance, the way a spray painting gun works. Consider two pipes shown in figures A and B. Essentially, pipe A is a diverging channel, while pipe B is a converging channel. In both cases, the fluid is input from the left and it exits from the right. With the kind of pipe A will work as a nozzle for supersonic flows. Sorry, pipe A will work as a diffuser for subsonic flows. Pipe B will work as a nozzle for supersonic flows. And B will work as a diffuser for supersonic flow. So this is like a pinching a hose pipe. Okay. So it will create supersonic flows, obviously. And it can also work as a diffuser for subsonic flows. Pipe B work as a nozzle for supersonic flows. No, it can't work as a nozzle because no, it can't be supersonic again. Okay, diffuser, it can be okay, diffuser. The logic follows simply from how to discuss leading to the D level nozzle. And converging channel behaves as a nozzle for subsonic flows. Converging channel behaves as a nozzle for subsonic flows and the diffuser for supersonic flows. Okay, this is a converging nozzle, right? And nozzle for subsonic flow and diffuser for supersonic flow. The reverse is true for diverging channels. Option B and D are correct. So these are some questions, model question. I'll come back to it later again. So fluid dynamics for astrophysics, this spherical symmetry study transonic solution for accretion and emission. So mass conservation is rho u r square. We have already seen that. Euler equation with body forces is 1 by rho d rho dr is minus 1 by c square gm bar square minus u by c square d u dr, right? So spherical symmetric study, this Euler force equation combining them will be d u dr u minus c square by u equal to c square by r minus gm bar square. So this is a typical form of Bondi accretion. I think you have gone across in the lecture video. If not, please go and see those videos again. This is the emission, solar wind emission, the accretion. If this start from here, it will go. It start from here, it will go directly there. It will go directly there. But if it starts from here, it will walk. It will act like this. Solar wind created from high temperature solar corona. Earth displays solar wind around and beyond via magnetic field. Charged particles follow B field lines determined by Lorentz force Q V perpendicular B is mv perpendicular square by Rg and Rg will be mv perpendicular by QB. This is the basically the cyclotron radius, radius of gyration, charge in a particle strength of A. So charge particles follow B field line apart, those slot lines travel till interstellar pressure balances with wind pressure. Causing signal by drop in temperature, B field direction change, increase in galactic cosmic ray. Voyager 1 August 2012 got helipause at 120 AU. For reference, Sun to Pluto is 39 AU. Okay, this is a heliopause at 120 AU. This is the distance the solar wind follows. You can see this is very large. Spherically symmetric steady transonic solution for accretion and emission. Solar winds are not spherically symmetric, carry B fields accelerated. Faster and tenuous, larger V, smaller density than isothermal prediction. The other equation of state, sun rotates, it doesn't start from rest. Incorporating rotation of sun and non-zero initial velocity, this will give us treatment of solution at perturbation of a Parker solution. And to check the stability of solutions, allow for del t. So rho r t is rho naught r plus rho hat r. It is the psi omega t. V is similar to I want to prove a small non-zero velocity t is equal to 0. It starts at rest. Real omega return solution is stable, waiting notice non-zero initial velocity. Rotation made this rho del t plus rho u dot grad u is minus grad p minus rho g plus f centrifugal. Fluid energy related to nuclear fusion 0.007 mpc square was done to bring object of mass m from infinite to surface. The acceleration g m star m by r star. Rs is 2 r star mc square. Rs is equal to g m star by c square. For bh, r star much less than rs. The acceleration much greater than mc square. Accretion releases much more energy than nuclear fusion. Not true for sun though. Okay. Interluminosity. It's a very important term we will come across. So in following matter, will explain radiation pressure from luminosity of central lobe compared to this is the highest available luminosity a certain mass of star can have. Outward radial force is this sigma TL by 4 pi r square c, while equal luminosity we know the integration of flux F radiation times ds radiation force is minus grad p rho alpha by c f rad rho k by c L by 4 pi s k energy plus radiated f dot 1 d by dt where k opacity fractional radiation absorbed P density of medium. Outer radial force is sigma TL by 4 pi square p inward gravitational force GMMP by r square at equilibrium interluminosity LN 4 pi CS semester MPC by sigma T if L greater than LN surrounding ionized hydrogen blown away. Accretion rate limit for interluminosity suppose m dot is the accretion rate let some fraction of accretion response radiated away some fraction of mass that is m dot. M dot some fraction of m dot. So is equal to epsilon m dot c square. If this is the luminosity. Then if more matter is activated, it will be blown away. This is the rate limit. If more matter is activated, it will be blown away. Accretion radius is r star 2g m star by v infinity square. Ke of the test particle infinity. Half m v naught is v infinity square compared to p on is activated g m star m by r. So flow property Bernoulli equation we know u square by 2 plus integration of dp by rho plus pi is constant. So if you need to prove this integration of dp by rho will be a square by gamma minus 1. How can you do this? So you need the formula of a square del p by del rho. So del p is the parametricity k rho to the power gamma. You get gamma p by rho. So dp, if you need dp, will get identify k r to the power 0. So integration of dp by rho will be this. Gamma minus 1 p by rho. So gamma p by rho is a square. This is the velocity. C square. Converse equation again this at r infinity is infinity 0 plus a infinity square by gamma minus 1 will be this. You get rho rs. I'll share this on with you. You can check and do your homework at your home. Converse equation is square by 2 plus integration of dp by rho plus pi is constant. So if r much greater than rb characterizes significant increases in pressure and sound speed. Rb is equal to 2g m star by infinity square. Also proportional to 1 by r square. For r greater than rb, equal to 1 by root r for r less than rb. In acceleration, supersonic regions can develop shock. Shock fronts convert supersonic flows to subsonic. To get by supersonic regimes smoothly, transonic flow requires a sonic point, thus gamma r. Why can't inflow matter with non-zero angular momentum flow? Spherical symmetric equation is a symmetric simple system implies conserved angular momentum. Spherical symmetry means central force. So V is equal to PR, F is minus grad V, and then this is equal to R cross P, the angular momentum, L dot will be 0. So spherical symmetry system implies conserved angular momentum. That's why in falling matter with non-zero angular momentum follow can't follow spherical symmetric equation. Because they will still have some angular momentum. Particles in a particles in stellar orbit around some compact object. Jm by r square is mb star mb5 square by r. This is v5. Empty. No radial velocity, no acceleration, model orbit of accreted objects at quasi Keplerian. If they are less than v5. Let's head on to the sample question assignment problems. Pick the correct statement. Quantity subscripts 1 and 2 represent pre-shock and post-shock values respectively. Other symbols follow the usual convention used in the course. P2 minus P1 by P1 is 2 gamma m square minus 1 by gamma minus 1. So which will be the conditions? We have already come across this. So I have explained because it is directly from the equation. That is 2 gamma m square minus 1 by gamma plus 1. You can see it also similar to CST square equals CS1 square plus how and E1 square C2 square. This is directly from the Rankine humanoid jump condition. So try to drive them if you want again. Consider an ideal monatomic gas passing through a normal solve. The upstream Mach number is 4. The upstream velocity is twice the downstream velocity. The downstream Mach number is 2 by 3, 2 by 5, 3 by root 8, 2 by root 5. So this is the downstream Mach number is this M2 is simply B e to m1 square. Upstream velocity is twice. Okay. So therefore, upstream velocity you will get simply from here this. Just divide this by you will get the velocity. Upstream velocity twice the downstream velocity. Okay. The downstream upstream velocity is twice, na. So twice the downstream. There will be 4. This will be minus 3. Minus 3 u2 square. So minus 3 by 2. Okay, minus 3 by 2. Minus 3 by 2. Minus 3 by 2. Gamma is 5 by 3. 2 by 3. Minus 3 by 2 times 2 by 3. So minus 1. 3 minus 1. Okay, minus u2 square. Okay. So if you divide by the u2 square, it will be this. It will be m2 square. This will be u2 square. U2 square is basically a half, right? So on what's up 4m1 square, 4m1 square, and then minus 1. It will be 2 by root 5. Do this calculation. Or on fulfillment. What is the spherical symmetric fluid wine type solution for transonic fluid? With the card statement, I will do some of the exercise in hand in my some of the later assignment solutions. Consider the spherical symmetric fluid wine type solution for transonic fluid. With the card statement, the location of the sonic point is independent of the gas temperature. The location of the sonic point depends upon the gas temperature. The dynamical equation remains same under changing the sign of gas velocity. All of the above statements are true. Okay. So, option B, the location of the sonic point RH depends on the sound speed of the medium and thus on the temperature. It depends on the gas temperature. The dynamical equation remains identical under V2 minus V. Then depend. So option B and C are correct. Location of sonic point independent of gas temperature. This is contradictory to B. This is wrong. 20 can't be. On the atmosphere of a spherically symmetric aspirated star, the steady state momentum equation for the stellar atmosphere is this. T is also given this. So the pressure at a given radius R is this. So you just need to calculate the pressure. So then the pressure at a given radius R is, you calculate the pressure, so it will be this. Still atmosphere is hydrostatic equilibrium false because you know that it's already the solar wind is there. Option A is correct. Next question, consider spherical acceleration by a compact astrophysical object with the current statement. The radiative force due to photons increase with an increase in the Thomson scattering cross section. The interaction rate for a star with a larger radius will be smaller. For a star, the larger radius will be larger. The radiative force due to photons decrease with an increase in the Thomson scattering cross section. So the two of them will be correct. Due to photons increase, then increase the Thomson scattering. Okay, and larger stars put out more energy, and they will be more luminous because they will equal to epsilon m dot c square. Okay, this is the thing. So because is the fraction of m dot that will go radiated, so it will be epsilon m dot c square. Okay, let's head on to some more questions. Yeah, I've given you that the options. The earlier question is given. Here it is given the answer. On an isolated star in space, you are told that a pressure in the atmosphere of the star behaves as E naught exp k r by r naught to the minus 5 by 7 minus 1. K is constant, r is the radial distance. With the correct answer, the atmosphere of the star is hydrostatic equilibrium. One would expect a wind to blow radially outwards from the surface of the star, obviously. One would expect a wind to be blowing radially outward inwards from infinity to the surface of the star. The atmosphere of the star cannot be in hydrostatic equilibrium. Option B will be correct because the pressure R is equal to R naught is greater than infinity. R is equal to R naught, it will be 1, right? So K minus 1, e to the power K minus 1, a positive number. So at R is equal to 1 naught, it is greater than at infinity, R is equal to infinity, it will be 0. The wind blowing radially outwards. Clearly, the atmosphere is not in hydrostatic equilibrium. Unlike an atmosphere in hydrostatic equilibrium, where the pressure decays exponentially, the pressure at infinity is non-zero. See? So, B and D are correct. See the solution for spherical equation Y and is in figure 1. The radial distance in spherical coordinates is on the x-axis and the square of the speed v square is on the y-axis. The vertical dashed line as RS denotes the sonic point and the horizontal dashed line marked A square RS denotes the square of the sound speed at the sonic point. Solutions can be divided into 6 broad categories as shown. Pick the correct statements. A square is equal to this. A square 4, 2, 6, 5, 1. So carbon can represent spherical symmetric transitioning accretion on a central black hole, not a star. All the families of curves shown here, 1, 2, 3, 4, 5, 6 denotes transonic solution. Curves belonging to family 3 and 4 can represent spherical symmetric accretion on the central star, not a black hole. Curve 2 can represent a spherical symmetric transonic wind blowing outwards from a star. So option A, the solution depended by carbon star or subsonic. Yeah, star has a subsonic, right? And it becomes supersonic. At larger radii passes through the sonic point and accelerates, becoming supersonic in the aperture small radii, and is appropriate for accretion onto a black hole. The solution depended by carb 2. Yeah, this carb 2 will be this from supersonic to subsonic. So with a small subsonic speed. Okay, sorry, it is transformed here. Subsonic speed. Passes through the sonic point and accelerates, becoming supersonic, travels outward to large radii as it is appropriate for a wind blowing outward. Only carbs 1 and 2 are transonic. Carb family 3, 4, although not transonic, can represent a gentle settling solution on the central star. All belonging to family 4 asteroids are infinity, so they cannot represent accretion. Refer again to figure 1, pick the card statement. The solution denoted by carbon can have spontaneous shock. Curves in family 5 and 6 are uncritical. Solution given by curve 2 can include dissipation due to viscosity. In solution 2, the pressure of the fluid at a small radii, probably the sonic point, exceeds the pressure at large radii. Answer will be B and D. Carbon passes smoothly through the sonic point, but definitely does not contain a discontinuous tension like a shock. 5 and 6 are unphysical. You can see 5 and 6. Solution period curve starts off with a small, we have already explained. Sorry, the solution frequency are double valued with a vertical, draw a vertical line at a given radius. They are double valued, right? It is double valued at a radius, single radius. They are unphysical. All the solution conserve the Bernoulli parameter, which is essentially the specific energy. There is no allowance for dissipation. Solution to each other at a small radius, the very small subsonic velocity. So all the specific energy in the internal energy would mean that the pressure is large. Has got compared to the kinetic energy of the fluid flow. The initial limit pertaining to accretion onto a central star or black hole is obtained by equating the inward gravitational force on a proton. If in the Mr. MP by R square with the outward force is greater on an electron by the radiation. You can read out the interaction rate for the star surface. So the interaction rate is needed. So you know the interaction rate M return is 4 pi MPC R star by sigma t. This is 90 10 to 26. It's about 1 kilometer. At 1 kilometer, it is this value. So option A is correct. Option A follows from this also M in relation to R star. Option D follows. And they are correct. Also the sketches A, B, and C shown in figure 2. The cross-sectional area of pipe A decreases from left to right, while that of pipe B increases from left to right. The cross-sectional area of pipe C initially decreases from left to right until it reaches a throat. After the throat increases, in all cases, the star can be thought to be at the left. So moving to the right would mean moving away from the stars. The correct statement A, B, and C. Near star, far from star. Transferring accretion to black hole with the gas at infinity starting out most straight. Option will be correct because it is accretion onto a black hole. A converging pipe accelerates fluid, right? Fluid at subsonic velocity, while a diverging pipe accelerates fluids at supersonic velocities. For transferring wind from a star with the gas starting out at trace, you would need a converging pipe to accelerate the fluid. It reaches the sound speed at the throat, after which you need the pipe to start diverging in order to keep accelerating the fluid. The same logic, if you reverse this, this will get that the transferring accretion onto a black hole. Okay. You see the figure from left to right. Subsonic will be supersonic. The pipe increases from left to right. This will be obviously subsonic to supersonic, near star to far from star. So this is correct. This is the typical day level nozzle. The reverse is true. So we have to like this. So give you some time if you So yeah. So let's head on to the next section, the disk accretion. I previously talked about the disk accretion, the cylindrical coordinates, quasi-Keplerian orbit. A gm by r square is mv phi square by r, or Vr much less than v phi. So the mass conservation, del dot del T plus del dot rho v is equal to 0. This holds. Del dot del T plus 1 by r del r r rho v r plus 1 by r del phi rho v phi is equal to 0. Del T integration of rho dz, so this will be 0. So you can see the circulation, the accretion of in falling mass over this cylindrical coordinates, right? So so then we see that, so then similar to this, we see that the del dot del T plus del dot rho v is 0, the mass conservations, and from here we get for the cylindrical coordinate del dot del T 1 by r is for the rho v 1 by r del r of r rho v r plus 1 by r del phi rho v phi. This will be 0, and this is cylindrical symmetry. And then this equation will be 1 by r del r of r integration of rho v r dz from minus infinity to plus infinity is 0, taking integration on both sides. So assuming no stratification of fluid over cylinder, no variation of radial velocity to z steady state, 1 by r del r of r rho v r to h is equal to 0, m dot is equal to minus 2 pi r rho v r dot to h, r rho v r h is m dot by 4 pi is equal to constant. Rho minus 2 pi r rho v r to h is the accretion rate, mass plus rho u, total mass accreted is rho u times L, right? So rho u, the area for a cylinder is 2 pi r times 2h, right? This will be minus 2 pi r rho v r 2h. U divided by vr. So momentum conservation, then again for statistical, we will get that rho u times grad u is equal to minus grad p plus rho g. Along z, we'll get 1 by rho d rho dpz dz is equal to gz is equal to grad phi at z del z is of gm by root over r square by z square. So we'll get at r much greater than h this. So along z, we'll get this along with the higher order terms. So momentum conservation for steady state accretion will be this, that 1 by rho pz by h is equal to minus dmh by r cube. So we'll get the rho c is square, h is equal to cs root over r by gm times r. So this is gr by v phi. So h by r is cs by v phi. For a thin accretion disk, fluid has to be very supersonic to be stable there. Along radial, using the grad of a dot b, we know this is the vector formula. For more reference, please see my mathematical prerequisite video. You have a clear idea. We have u dot grad u equal to grad u square by 2 minus u cross curl of u curl of u is equal to 1 by r hat, r theta hat, z hat, del r, del theta, del z, u r u theta is 0, equal to z hat by r, del r u theta minus del theta u r, z hat theta by r plus del r u theta minus del theta u r. This u square is equal to u theta square plus u r square. Momentum conservation expression is rho u dot grad u is equal to minus grad p plus rho g along radial. So u cross curl of u is u r u theta by r plus u r del r u theta minus u r del theta u r of r cross z hat plus u theta square by r plus u theta del r u theta minus u theta del theta u r is theta cap cross z cap r hat. Thus we'll get this equation. Moment of conservation of steady state equation will get that rho u dot grad u is equal to minus grad p plus rho g along radial. Substituting in momentum equation will get neglecting this term that u r del u r. So similarly del r u r square is order of u r square is approximately 0. We will negate this term. Consistency for quasi-Keplerian injection. The more Kepler in the orbit, the smaller the radial velocity. Along azimuthal component v phi is root over gm by r. M is the mass of black hole accretion. So we'll get a differential velocity due to gravitational forces, shear forces, drag, viscosity, and dissipation. And then this heats up and radiates. Specific angular momentum v theta r is equal to root over any momentum lost to accrete via viscosity. So momentum lost will be happened via viscosity force. Then these terms will come. Again, the quasi-Keplerian orbit will get this tr theta. Will get some big term. I'll share these notes with you. So main thing is the energy distributed via viscous force will d, that is 3 by 8 by dm dot by r cube. The equation is enabled by viscosity. It is equal to 2 by 3 m dot by h. Equation time scales are smaller than EP renormalization time scales. 2 temperature plasma is collisionless P can exceed H. The 2 temperature plasma. Later we need these kind of things for model. Shocks and particle acceleration. Thermal particles assigned a temperature determines distribution. This is the distribution formula. This is standard Maxwell Boltzmann distribution. Particles can be boosted by non-thermal processes. Shock nisku the thermal population. Non-thermal days power law follow up for non-thermal population, that is n proportional to the minus alpha. What can cause such a distribution? Inelastic collision in a region with scattering centers, weakening charge particles, etc. After k collision, u is equal to beta to the power k e naught, n is equal to n naught p to the power k. Shocks and particle acceleration is equal to n naught by e to the minus alpha. This larger number of scattering, high energy, lower population, low approaching collision, and opposite catching up collision. So diffusive shock acceleration will be the DSA, the important phenomena. Diffusive shock acceleration in lab time shock moves at velocity u assumes SCs in both sides of shocks. In shock frame, this is the post shock. The shock front propagate this side is the pre-shock. VSU V2 U by 4. In pre-shocked fluid frame, this is the post-shocked shock front, pre-shocked V10 because we are seeing from the pre-shocked frame, and it is now going this fluid is this side. Because V2 is now 3 by 4 U because V1 is 0. Okay, earlier V1 is U, so we are seeing that it is going to U by 4 because it is more, so you will see that it will coming towards us by 3 by 4 U velocity. Diffuse shock acceleration is approaching collision test particle gain energy. Some of these energetic particle diffuse in post-shocked fluid frame. Post-shocked is V2 is 0, test particle shock front pre-shocked V1 is equal to 3 by 4 U scattering center. Let's return to the sample problem, assignment problem. Correct option, conjure spherical accretion onto the compared astrophysical object in the polytropic index of the accreting Siemens constant shock formation is not possible. Is right or not? Same shock formation is possible. Equatorial surface around the compact star, the central object for a binary star system sustaining an accretion is perfectly circular. The Lagrangian first Lagrangian point is situated on the innermost equipotential surface of a compact binary. So you can see that the spherical accretion and comparatively the polarity index of the accreting gas remains constant. The shock formation is not possible. And the first Lagrangian point is like the Aditya Elon mission. The first Lagrangian point is in between the Earth and Sun. So innermost equipotential surface of a compact binary. So right options are A and D. Question number 2 is consider the gas from a large star being accreted by its compact companion through a quasi-Keplerian accretion disk. The accreting gas has some initial angular momentum. Accretion can proceed even if the gas particles in the disk have zero radial velocity. A gas particle in this quasi-Keplerian accretion disk with a finite accretion rate will have a small inwardly directed radial velocity. The specific angular momentum per unit mass of a gas parcel in a quasi-Keplerian accretion disk at radius r1 is greater than that at radius r2 if r1 greater than r2. The specific angular momentum per unit mass of a gas parcel in a quasi-Keplerian accretion disk at radius r1 is greater than that at radius r2 if r1 less than r2. So we'll have that option B and C are correct because a gas parcel, option is correct because for a quasi-Keplerian accretion disk there must be non-zero radial velocity of the infalling gas. Otherwise, there will not be any accretion. The specific angular momentum for such an accretion is proportional to root r. Option C is correct. B and C are correct option. Consider steady state quasi-Keplerian accretion disk around the compact object. So choose the correct option is the angular momentum per unit mass of the gas particle about the analogy in the center of the compact object root r. And second option is just proportional to r. Turbulent it is envisaged in the Sakura-Tsunai prescription will be subsonic. Sakura-Tsunai prescription the visco turbulent it is can be supersonic. Option A is correct. As we discussed earlier, it is proportional to root r. The angular momentum about the origin of the cylindrical coordinate system about the compact object is proportional to root r. In a Sakura-Tsunai viscosity prescription, the speed of the radius cannot exceed the sound speed, which is why alpha less than 1. So option A and C are correct option. Consider a thin quasi-Keplerian accretion disk with a constant m dot. The dissipation rate per unit cross section at a certain radius r1 is d1 and at another radius r2 is d2. So d2 is equal to 4 d1 if r1 is equal to 2 r2. d2 is equal to 2 d1 if r2 is equal to 2 r1. dt is equal to 8 d1 if r1 is equal to r2. The disk height 8 is proportional to r to the power 3 by 2. Okay. So answer C and D will be right option because the viscous dissipation rate per unit area is given by dr 3 by 8 by gmm dot by rq. So it is clear that option C is correct. Would know that for a thin disk is hence option D is also correct. We already have discussed all of this. I am just recapping for your satisfaction. Correct statement: viscous dissipation primarily hits photons with an exchange energy with electrons. Directly hits electrons. Sakura-Tsunai prescription: the viscous stress can exceed the gas pressure, cannot exceed the gas pressure. So option is correct because viscosity being a momentum-based process acts preferentially on the heavier species because it's a momentum-based. So higher photon has the higher mass. So by definition, level less than 1, the viscous stress can never exceed the pressure. Okay. So these are the all questions. Let's move to the next. Some two more questions. Accretion disks are formed when gas supplied with some initial angular momentum is forced to accrete onto a massive central object. Pick the correct statements regarding disk accretion. A gas parcel in a quasi-Keplerian accretion disk with a finite accretion rate will have a small inwardly directed radial velocity. A gas parcel in an accretion disk with a finite accretion rate can have an azimuthal velocity that is equally exactly to the Keplerian value. The specific angular momentum per unit mass of a gas parcel in a quasi-Keplerian accretion disk radius r1 is greater than that at radius r2. If r1 greater than r2. The specific angular momentum per unit mass of a gas parcel in a quasi-Keplerian accretion disk at radius r1 is lesser than that at radius r2 if r1 greater than r2. So option A and C are correct because option A is correct since there needs to be a radial velocity for accretion to happen. M dot proportional to R rho VR H for a cylindrical shell of height H, where rho is the mass density and VR is the inwardly. So you understand that the azimuthal velocity is Keplerian. So and we already denote is root R. Option A and C are correct. Correct statement. Again, similar question already come across this. Shear viscosity in accretion disk enables gas parcels at large radius to lose angular momentum. They are following not. Is correct by definition. Option C, option B is option C. Let's see. Two compact objects A and B have accretion disks around them. The compact objects are equal in mass, and the rate at which the gases feed into the respective accretion disk at the outer radius is the same. Do you think about the same coefficient conductive viscosity of the gas in significantly higher than viscosity of space more than B? I studied option C of the previous question. The specific angular momentum increases in increasing radius. So it needs to be lost in order to gas to settle to accurate. Option B correct because dissipation goes into hand with the viscosity. Radial involved velocity. When you kinematic viscosity coefficient, so option D is correct. Assume that the local disk height in an accretion disk is proportional to the local radius. Is proportional to R. The accretion rate is constant throughout the day. It doesn't vary with radius. Assume the radial velocity is proportional to R minus P. Pick the correct statement. If bigger than 2, the gas density in the accretion disk will decrease with decreasing radius. The density closer to the center of it is smaller than that further from it. Greater than 2, this is follows. So option A is correct as m dot is R proportional to R over H. If proportional to R, this becomes m dot is equal to K R square over R. So K is a constant. If V are proportional to this, the rho will have to increase within R in order to keep m dot constant. When we have seen this, is said rho is equal to rho naught R to the power Q. M dot doesn't depend on R, so Q is equal to P by S to positive number. Let's hold on to here sometime. So let's head on to the next one. So you understand now this one that m dot doesn't depend on r. So q is equal to p minus 2, which is a positive number. So option A and C are correct. P is equal to 2. The gas density in exchange is constant. H q is equal to 0. So rho doesn't depend on. So rho doesn't depend on r then. We know that the Bernoulli parameter is defined as b is equal to half v square plus p by rho minus phi, where phi is the gravitational defined as b is equal to half v square plus p by rho minus phi, where phi is the gravitational potential. So which one is the correct statement? If the Bernoulli parameter of the gas in the active center is positive, we can be sure that no part of the accreting gas can escape. All of it has to accrete onto the central object. If the Bernoulli parameter of the gas in the active center is negative, you can be sure that no part of the accreting gas can escape. All of it has to accrete on the central object. If the Bernoulli parameter of the gas in the active center is positive, the accreting gas is unbound and there can be a wind emanating surface of the disk that carries of matter to infinity. The Bernoulli parameter of the accreting gas has no relation into the presence or absence of a wind from the disk. By definition of the Bernoulli parameter, if B is positive, it means that the accreting gas is not gravitationally bound and there can be a wind. So option B and C are correct. Third statement, one can expect to rotate accelerated particles in the vicinity of a shock, right? One can expect the gas in the vicinity of the shock to be relatively cooler than gas far away from the shock. That is wrong because that will be hotter. This is the inverse. Particles need to diffusively cross the shock front multiple times in order to gain energy and get accelerated. Yes, that's what diffusive shock extension is about. One can expect the gas in the vicinity of the shock to be relatively hotter than gas far away. Yeah, the correct option. So this we get the. So let's give some time for others. See. Meanwhile, I will start some of the 9 about the blast wave. What are the blast waves? Blast waves are spherical blast waves like supernova, large energy deposition at a point, or self-similar propagation of shocks. That is spherical blast wave. Stellar days, they are like main sequence stars burn hydrogen outward pressure from the reactions balance gravitational pull. When very heavy stars die, core collapse. When solar mass stars die, hydrogen is burned in outer layers instead of core. Star blows up to a red giant. Unstable stellar winds blow outer layers off as planetary nebula, leaving behind white dwarf. Stellar death is white dwarfs, core of carbon and oxygen, thin layer of H by H, very compact, very heavy stellar remnant acted material from a companion. At a certain mass limit, white dwarf core reaches high temperature from gravitational pressure, igniting runaway C fusion. Why is it a runaway process? In stars expand when temperature increases to balance gravitational thermonuclear processes. In white dwarf, intensity pressure stabilizes gravitational pull and depth of temperature. As C fusion adjusts temperature, white dwarf does not expand thermal runaway until too late, it will be supernova. And shock condition. As a result of injection of energy E into a point in medium, rho on pion depends on E release into blast shock. As of noticeable, this is the some properties of the spherical blast wave. Self-similar shocks that blast scales as lambda with time. Okay, the lambda is this. Similarity variable is this. Shock radius goes at 0 to 5, agrees with data. This is from the data. And also from the direction analysis. Shock velocity goes with 2 minus 3 by 5. This is purely from Newtonian perspective. So U2 by U shock is 2 by gamma plus 1 in shock frame, rho 2 by rho 1, gamma plus 1 by gamma plus 1 m square. This we have already done this. This is the pre-shock, this is the post-shock. This is the pre-shock, this is the post-shock. Lab frame, this in shock frame E1 is 0 and U2 is 3 by 4 E1. Rho P2 is equal to 2 by rho h rho 1 U shock square in shock frame. P2 by P1 2 gamma plus 1 m square minus 1 plus 1, right? So P2 will be this 2 by gamma plus 1 U shock square rho 1. Conjugation equation dimensional variables so that rho RT is rho 2 rho prime CS is this. So you can show this, just derive this and derive the base of will be simple from the set of two last two weeks. This. So these are from some homework. I'll upload this and try to do this. I have most of them. We have done the answers to most of the homeworks. Just for you to do and check with the answer. Del del t plus 1 by r. This is the cylindrical coordinate. We have the 0. We got the conjugation equation. Then log p by root to the power gamma is 0. Then we head on to the magnetohydrodynamics. Fluid dynamics, imagine magnetic fields, fluid treatment on particle orbits, work on quartz grained scales, RG tends to 0. Separate charges indistinguishable, neutral plasma, plasma is isotropic, sigma is scalar, infinite quantitivity, vanishing electric fields, finite current, J is equal to sigma E, infinite mobility of electron, no potential gradient, can develop as a response to an external field, sigma E in fluid frame. Immediate induction equation, Maxwell's equation is this. Okay. So you'll have a new tensor. This is the lab in the fluid frame. Lorentz transformation of EM fields is this. F prime mu nu is lambda mu rho lambda nu sigma F rho sigma is the treatment tensor treatment field distinct tensor Lorentz transformation by boost along X. Okay, the Maxwell equations. Also called as the imaged induction equation. We will drive those equations from here. P1 prime is on, we know B1 prime B parallel, prime is B parallel. B perpendicular prime is this, B perpendicular prime is this. So we'll get the E perpendicular is minus B cross B by C. A non-relativistic field lab is 0. Using curl P is equal to minus 1 by C del B del T. Induction equation is del B del T. H curl of B cross B. This is the induction equation. Okay. Kinetic induction equation. Curl del B del T. H curl of B cross B. Negative fields in a fluid is given below. Immediate induction equation will be curl of P is 1 by C del T. Induction equation is this. We will get an initial term lambda del square B. Correction term for finite conductivity as lambda is equal to C square 4 pi sigma C. Distribution of B flux will be this V by lambda similar to this, depending on potential decay with time. Perfectly conducting fluid or non-relativistic infinitely conducting fluid. No source or no sink, so del dot J is 0. Perfectly conducting fluid availability is this. Conjugation of del dot B 0, not given by image, but rather its conservation. So assignment problems. The following image shows V-shaped structure near the nose and tail of an aircraft moving at supersonic speed. The correct option. See, an observable here is sonic boom. So we'll have the observable sonic boom when the V-shaped structure passed him or her. The V-shaped space structure represents a shock, obviously. And this is wrong, this is wrong. On the following image, it shows radio emission from a supernova cell. The parts of the image that are red represent the highest intensity, the parts in yellow represent the next high level intensity, and the parts in blue represent relatively low intensities. The particle density in the red areas should be lower in compared to the density in the blue area. Areas should be higher in compared to the density in the blue area. So right option, see in the plot. See, option B and C are the correct. Because it's a supernova explosion. The spherical blast to be against a similar solution. And then the 22 T greater than T1. The energy content in the blast wave at T2 is greater than, so we know that it is constant. So the theorem underlying the is that there is no energy dissipation, energy remains constant. So option C. Energy applicable following this scale that are much smaller than the charge dispersion length scale. Which one? Immediate deals energy is applicable for length scale that are much larger than the charge separation length scale. Is applicable for frequency that are much lower than the plasma frequency. That's yes, correct. Very induction equation is del B del T, Carl B cross B plus eta del H square B. The rotations have their usual meanings and eta is magnetic divisibility. The correct options will be answer B and D. The magnetic errors number is L V by eta, so at large Rm. The second term becomes negligible and the first terms assumes importance. Second term is indeed responsible for the decay of magnetic fields. Okay, so option B and D are the correct option. Give you some time here. This is the term. Let's head on to the some of the. So, in dealing with the derivative expansion phase of supernova shocks, you have used a self-similar variable zeta, which is a unique combination of the special variable r and time t proportional to r proportional to the minus 2 by 5. So, what are the correct options? Turning to such a self-similar variable enables us to work with a set of coupled differential. So, we'll come to it in the next time. Okay. For now, so again with the current, we'll be using E is equal to minus B cross B by C these terms. But first, momentum equation. But so I hope you understand this. The immediate induction equation. By the notation have the usual meanings of eta, magnetic diffusivity. Magnetic Reynolds number Rm is equal to LV by eta. So at large Rm, the second term becomes negligible and the first term assumes importance. The second term is indeed responsible for the decay of magnetic fields. Okay. Option B, the second term on the right hand side of the equation, eta is equal to govern the decay of B. The last term, the magnetic Reynolds number. The first term on the right hand side of the equation is important high magnetic Reynolds number. Okay. So B and D are correct in that aspect. So now 4 is again these are the MSD question. MSD is applicable for length scale that is much larger than the charge separation length scale. Charge separation length scale is very small, so MSD is applicable for much higher, larger length scales, not that atomic kind of length scale, and it is applicable for frequency that is lower than the plasma frequency. So you have seen the magnetic induction equation. This is the plot. So you can see the induction equation. 1 by C 4 pi J minus del T equals B by C square. The induction equation for non-relativity infinitely conducting fluid, no source or sink. So delta J is 0. Conducting fluid is del delta is curl of M cross B. Listen. So I think somewhere diffusion equation broadens and decays with time. See, this is the diffusion equation similar to our inertial by viscous. The charge finite conductivity. So this is valid for only this induction equation. Okay. So let's come back to it. The time next. Till then. Okay, so let's meet next time. So we'll talk about it more later and talk about this different kind of Blastoise. I actually personal work, my personal PhD work, some of mine relies on this kind of topics, and I have presented a paper on this. That is yet to submit. That is yet to publish in the journal. So let's meet next time, and we'll talk more about it.